Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll walk you through the fundamentals of Amazon Elastic Container Service, or ECS, a fully managed container orchestration service that lets you easily run, scale, and secure Docker containers in the cloud. We'll cover the key concepts, core components, and deployment patterns that set ECS apart. You'll gain a clear understanding of how ECS integrates with the broader AWS ecosystem, including networking, security, scaling, and observability, so you can confidently start building production-grade containerized applications. Let's get started. As modern applications shift toward microservices and distributed architectures, managing containers at scale becomes a real challenge. This is where container orchestration comes in. It's a critical capability that automates the deployment, scaling, and management of containerized applications across clusters of compute resources. At its core, container orchestration handles the entire container lifecycle, from starting and stopping containers to rescheduling them on healthy infrastructure when failures occur. This removes the burden of manual intervention and ensures higher availability for your services. One of the most powerful aspects of orchestration is its ability to abstract infrastructure complexity. Developers no longer need to worry about which instance a container is running on or how to manually wire up services. Instead, they declare what they want, and the orchestrator takes care of making that happen, continuously maintaining the desired state. It also enables scalability and high availability. As traffic grows, the orchestrator can automatically launch more containers to meet demand, and when things quiet down, scale back down to save resources. This elasticity is essential for cost-effective cloud-native operations. Service discovery and networking are handled automatically as well. As containers come and go, the orchestration system keeps track of them, wiring up internal DNS names, or integrating with load balancers so that services can always find and talk to each other. Beyond just running containers, orchestration systems help with resource optimization. By intelligently packing containers based on their CPU and memory needs, they maximize utilization of underlying infrastructure, reducing waste and cost. Finally, orchestration supports rolling updates and rollbacks. You can deploy new versions of your services gradually, one container at a time, without downtime. And if something goes wrong, the system can automatically roll back to a healthy state. Amazon Elastic Container Service, or ECS, is AWS's fully managed container orchestration service. It simplifies the process of deploying, managing, and scaling containerized applications so you can focus on building and running your services, not managing infrastructure. With ECS, you don't have to worry about setting up or maintaining the orchestration control plane. AWS handles all of that for you, offering a highly available and scalable backend that's battle-tested at massive scale. This makes ECS an excellent choice for teams looking to reduce operational overhead without compromising on power or flexibility. One of ECS's core strengths is flexibility in compute options. You can choose to run your containers on EC2 instances if you need fine-grained control over the underlying infrastructure. Or, for a completely serverless experience, you can use AWS Fargate, which allows you to run containers without managing any servers at all. Applications in ECS are modeled using task definitions, which group one or more containers with shared resource definitions and runtime configurations. ECS supports robust auto-scaling capabilities. If you're using EC2-backed clusters, ECS also supports cluster auto-scaling, so your infrastructure adapts dynamically to the needs of your workloads. Through built-in integration with Elastic Load Balancing and AWS Cloud Map, ECS provides automatic service discovery, DNS resolution, and seamless load balancing. Finally, ECS also features deep integration with the broader AWS ecosystem. You get native support for IAM for access control, CloudWatch for observability, CloudTrail for auditing, Secrets Manager for secure credential storage, and tight integration with VPC networking, enabling secure and scalable container networking. To understand how Amazon ECS works, it's important to get familiar with its core components, the building blocks that orchestrate containerized workloads in a scalable and efficient way. First, we have the cluster. A cluster is a logical grouping of compute resources where your containers will run. These resources could be EC2 instances that you manage yourself, or Fargate managed capacity, where AWS handles the infrastructure. Next is the task definition. This is the blueprint for your application. It specifies everything ECS needs to run your containers. The image to use, to how much CPU and memory each container requires, environment variables, networking mode, port mappings, and any IAM roles needed for access to AWS resources. A task is simply a running instance of that task definition. It represents one or more containers deployed together on the same host. Tasks are the basic unit of deployment and scaling in ECS. You can run multiple copies of the same task across your cluster to handle varying loads. To manage these tasks effectively, ECS provides a construct called a service. A service ensures that a specified number of tasks are always running and healthy. It automatically replaces failed tasks, handles rolling deployments of new versions, and can integrate with elastic load balancers to distribute traffic across containers. The launch type defines how your tasks run, either on EC2 instances that you provision and manage, or on Fargate, where AWS provisions and manages compute for you behind the scenes. For tasks running on EC2, ECS uses a container agent. This lightweight daemon runs on each EC2 instance in your cluster and acts as a bridge between the ECS control plane and the compute instance. With Fargate, this component is fully abstracted away. When tasks are started, the ECS scheduler is responsible for placing them onto available infrastructure. It uses configurable strategies like binpack, random, or spread across availability zones to optimize placement and availability. Finally, ECS includes native service discovery. Using AWS Cloud Map or internal DNS, ECS enables your services to find and communicate with each other dynamically, which is essential for microservices-based applications. When deploying containers with Amazon ECS, you have two primary launch types to choose from, EC2 and Fargate, each offering distinct advantages depending on your use case. Let's start with the EC2 launch type. With this option, you provision and manage your own fleet of Amazon EC2 instances, which act the underlying infrastructure for your containers. This gives you full control. You choose the instance types, configure storage, install custom AMIs, and even attach GPUs for high-performance workloads. This is ideal when you need deep customization, cost optimization at scale using reserved or spot instances, or when you already have existing EC2-based infrastructure in place. On the other hand, AWS Fargate is a serverless compute engine for containers. It abstracts away the infrastructure layer entirely. You don't provision, scale, or patch any EC2 instances. Instead, you define the task requirements, such as CPU and memory, and Fargate launches the containers for you. This dramatically reduces operational overhead and allows teams to focus purely on building and deploying applications. When it comes to scaling, the two models differ. With EC2, you need to manage auto-scaling groups to ensure your cluster has enough compute capacity for your tasks. In contrast, Fargate automatically scales container execution based on task count. No need to worry about instance limits or provisioning delays. Task startup times are generally faster with Fargate since there's no dependency on EC2 instance availability. This makes Fargate well-suited for bursty, event-driven workloads like data processing jobs or short-lived microservices. From a security and isolation standpoint, both launch types support IAM roles for tasks, VPC networking, and security groups. However, Fargate offers stronger isolation by running each task in its own lightweight virtual machine, further reducing the attack surface. Finally, consider the cost model. EC2 is priced at the instance level. You pay for the uptime of the instances you manage, regardless of how much of their capacity is used. With Fargate, you pay per second for only the CPU and memory you allocate to each task, which can be more cost-efficient for variable workloads. In summary, EC2 is best when you need customization and control, while Fargate is ideal for teams looking to minimize infrastructure management and move fast with containerized workloads. In this illustration, we're comparing two key launch types in Amazon ECS, EC2 launch type and Fargate launch type, which determine how the underlying compute resources for your containers are managed. On the left side, we have the EC2 launch type architecture. In this setup, the ECS service within the ECS account is responsible for managing containerized tasks. However, the customer needs to manage the EC2 instances that act as the physical infrastructure for running these containers. These EC2 instances are provisioned in the customer account where they reside within a VPC for network isolation. ECS schedules tasks on the EC2 instances based on available resources. Each container task is assigned an Elastic Network Interface (ENI), which allows for secure and scalable network communication. This approach provides you with control over the EC2 instances, such as selecting instance types, configuring auto-scaling, and managing other resources, but requires more responsibility in terms of infrastructure management. On the right, we have the Fargate launch type architecture. Here, the ECS service still operates within the ECS account, but rather than managing EC2 instances, AWS Fargate abstracts away the underlying infrastructure. Fargate automatically provisions the compute resources necessary to run container tasks without requiring customers to manage the servers. The customer still defines the VPC for network isolation, and each task is still assigned an ENI for secure connectivity, just like in the EC2 model. However, Fargate eliminates the need for server management. You no longer need to worry about choosing EC2 instance types or scaling infrastructure. Fargate dynamically allocates the compute resources based on task requirements and scales them as needed. At the heart of running any application on Amazon ECS is the task definition, a critical building block that acts as a blueprint for your containerized workloads. A task definition tells ECS exactly how to run your application. It specifies everything from the Docker image to use, to how much CPU and memory to allocate, how containers should interact, and how networking should be configured. It's your complete declaration of intent for what the application environment should look like. Each task definition can include one or more containers. These containers are scheduled together on the same host and can share resources like networking and storage. This is particularly useful when you have tightly coupled services, for example, a main application container and a sidecar for logging or proxying. You can also define resource requirements for both the task and individual containers. Specifying CPU and memory limits ensures ECS can place the task appropriately across your cluster and prevents resource contention. To securely configure your containers, task definitions let you pass in environment variables and securely reference secrets from AWS Secrets Manager or Systems Manager Parameter Store. This allows you to externalize configuration and avoid hard-coding sensitive information. You can also define port mappings that control which container ports are exposed and how they map to the host or VPC network, which is essential for service-to-service communication and load balancing. Finally, two key IAM roles are specified in the task definition. The execution role is used by ECS to pull container images and push logs to CloudWatch. The task role, on the other hand, is assumed by the running containers and is used to interact with AWS services like S3 or DynamoDB, giving you fine-grained access control over what your application can do. Once you've defined how your containers should run using a task definition, the next step is to ensure those containers stay running reliably over time. This is where ECS services come into play. An ECS service is responsible for managing the long-term lifecycle of your tasks. You specify how many copies or desired count of your task should be running, and ECS ensures that this number is maintained. When it comes to deploying new versions of your application, ECS offers flexible deployment types. The default is a rolling update, where ECS gradually replaces old tasks with new ones while maintaining service availability. ECS services can be tightly integrated with Elastic Load Balancing, whether it's an application load balancer, network load balancer, or gateway load balancer. This enables automatic traffic distribution across your running tasks and ensures seamless scaling as demand changes. To handle fluctuating workloads, ECS supports service auto-scaling. You can define scaling policies based on CPU or memory utilization, ensuring that your application scales up during peak load and scales down to save costs when demand drops. For more advanced scheduling, ECS provides placement strategies and constraints, allowing you to control how tasks are distributed across EC2 instances or availability zones. You can enforce spreading for high availability, bin packing for resource efficiency, or restrict deployments based on attributes like instance type or custom tags. You also get powerful tools for governance and security. ECS services support resource tagging for tracking costs and organizing deployments. In addition, fine-grained IAM policies let you control who can create, update, or delete services. Lastly, ECS includes a deployment circuit breaker feature. This allows automatic rollback of deployments if a certain threshold of failures is detected, reducing the impact of faulty releases and improving operational confidence. Integrating Amazon ECS with a robust CI/CD pipeline is key to accelerating software delivery, improving reliability, and minimizing human error. It all begins with automated image builds. Every time a developer pushes code, a CI tool like AWS Code Build, Jenkins, GitHub Actions, or GitLab CI can be triggered to build a new container image. Once built, this image is pushed to Amazon Elastic Container Registry, or ECR, making it instantly available to ECS. From there, you can implement infrastructure as code using tools like AWS CloudFormation, the AWS CDK, or Terraform. These tools allow you to version control your ECS services, task definitions, networking configurations, and more, ensuring your deployments are repeatable, traceable, and easy to manage across environments. As part of the pipeline, you can automatically register new task definitions. This step updates the ECS configuration with the latest image version and parameters using scripts or AWS CLI commands. By doing this programmatically, you reduce manual overhead and ensure consistency across deployments. When it's time to release, automated deployments come into play. You can use native ECS rolling updates or integrate with AWS Code Deploy to perform blue-green deployments, where traffic is gradually shifted to the new version while the old one stays online. If any issues are detected, the deployment can be rolled back automatically, ensuring minimal downtime. Approval gates add another layer of control. Before deploying to production, your pipeline can pause and wait for a manual approval or run a battery of automated tests. This gives teams a chance to validate deployments and enforce compliance before changes go live. Finally, well-structured pipelines can support multi-environment deployments. By parameterizing your workflows, you can deploy to dev, staging, and production ECS clusters in a controlled manner, using different configurations, task definitions, or IAM roles per environment. One of the key strengths of Amazon ECS is its ability to scale containerized workloads dynamically and route traffic efficiently. With ECS, you can configure services to scale in or out automatically based on real-time resource usage. Common triggers include CPU and memory utilization, but you can also scale based on custom CloudWatch metrics. In addition to reactive scaling, ECS supports scheduled scaling. This is especially useful when your traffic follows predictable patterns, optimizing cost without sacrificing performance. Target tracking scaling policies make this even easier. You simply define a desired metric target, and ECS handles the rest. It continuously monitors and adjusts the number of tasks to stay as close to the target as possible. Now let's talk about load balancing. ECS integrates seamlessly with both application load balancers and network load balancers. These load balancers distribute incoming traffic evenly across healthy tasks, providing fault tolerance and scalability out of the box. With dynamic port mapping, especially when using the AWS VPC or bridge network modes, ECS can assign unique ports to each container on the same host. This allows multiple instances of the same service to run side by side without conflict, crucial for high-density deployments. To ensure traffic only reaches healthy containers, ECS works with load balancers to perform health check-based deregistration. If a task fails its health check, it's automatically removed from the load balancer's target group and replaced, improving reliability without manual intervention. Finally, capacity providers offer a flexible way to manage scaling at the infrastructure layer. Whether you're running on EC2, AWS Fargate, or a mix of both, including spot instances, capacity providers let you control how and where your tasks are launched, enabling intelligent, cost-effective scaling across environments. At the foundation is AWS Identity and Access Management, IAM. ECS leverages IAM to define and enforce fine-grained permissions, controlling who can create, update, or delete ECS services, task definitions, and more. This enables strong governance while maintaining agility. A particularly powerful security feature is task roles, IAM roles that are assigned directly to ECS tasks. These roles allow containers to access other AWS services such as S3, DynamoDB, or Secrets Manager, using least privilege permissions. In terms of encryption, ECS supports data at rest and in transit, whether it's encrypting attached storage volumes like EBS or securing communication channels using TLS. You can ensure sensitive data stays protected throughout its lifecycle. Networking in ECS is also built with security in mind. ECS tasks run inside your Amazon Virtual Private Cloud, VPC, giving you full control over traffic using security groups, network ACLs, and route tables. Handling sensitive data like API keys, passwords, and configuration values is simplified with secrets management. ECS integrates with both AWS Secrets Manager and SSM, letting you securely inject secrets into containers at runtime without baking them into images. To protect your container images, Amazon ECR supports image scanning via Amazon Inspector. It automatically detects vulnerabilities in your container images, helping you catch and address security issues before they ever reach production. You can also enable image signing to ensure that only verified, trusted images are deployed. For observability and audits, ECS integrates with AWS CloudTrail, CloudWatch logs, and AWS Config, providing full visibility into API activity, system events, and configuration changes, essential for forensic analysis and compliance reporting. Lastly, ECS and its underlying infrastructure are certified for a wide range of industry standards, including SOC 2, ISO 27001 HIPAA, and PCI DSS, making it suitable for running even the most regulated workloads. When considering Amazon ECS for your container workloads, it's important to understand how pricing works. And the good news is, it's designed to be transparent and flexible. First, let's start with the ECS control plane itself. ECS is free to use. There's no additional charge for orchestrating your containers. You only pay for the underlying compute, storage, and networking resources that your applications consume. If you choose the EC2 launch type, you're responsible for managing and provisioning the EC2 instances. In this model, you're billed for those instances based on standard EC2 pricing. This approach offers greater control over the infrastructure, and you can optimize for cost using EC2 savings strategies. With the Fargate launch type, there's no need to provision or manage servers. Instead, you're billed per second based on the vCPU and memory resources that your containers request. To optimize costs further, Fargate Spot is available for workloads that can tolerate interruptions. It offers the same ease of use as regular Fargate, but at up to 70% lower cost, making it perfect for batch jobs. If you're using Amazon ECR to store your container images, you'll pay for image storage and for data transfer out, such as when pulling images into ECS tasks. If your ECS services are integrated with an application load balancer or network load balancer, you'll be charged based on the number of new and active connections and the load balancer capacity units, or LCUs, used. In terms of observability, CloudWatch logs, AWS X-Ray, and CloudTrail help you monitor, trace, and audit your ECS environment. These services incur additional charges based on data volume and retention. Lastly, consider savings plans or reserved instances to significantly reduce compute costs for ECS workloads running on EC2 or Fargate. These pricing models offer long-term discounts in exchange for committed usage and can drive substantial savings at scale. When running containerized applications at scale, keeping your cloud costs under control is just as critical as ensuring performance. Let's start with Fargate Spot. This launch option allows you to run fault-tolerant workloads at a steep discount, often up to 70% lower than regular Fargate pricing. It's an excellent choice for workloads like batch processing or background jobs where interruptions are acceptable. Next, consider how you define your containers. By right-sizing your task definitions, you avoid paying for unused resources. Service auto-scaling is another powerful cost control tool. Instead of provisioning resources for peak load 24/7, you can scale task counts up or down automatically based on real-time demand using CloudWatch metrics. For EC2-based ECS deployments, compute savings plans and reserved instances offer substantial savings, often up to 72% over on-demand pricing, in exchange for a commitment of usage over 1 or 3 years. They're ideal for predictable steady-state workloads. Then there's container image optimization. Trimming your container images down by removing unused packages and dependencies not only reduces ECR storage costs, but also speeds up container start times, which can indirectly save compute costs. Another effective strategy is to analyze and fine-tune scaling behavior using CloudWatch. Dive into metrics like CPU and memory utilization to adjust your scaling policies and avoid unnecessary over-provisioning. For those using the EC2 launch type, task placement strategies like bin packing can significantly improve instance utilization. ECS can pack tasks onto the fewest number of instances, helping you run more workloads with less infrastructure. Finally, don't forget to clean up your Amazon ECR repositories. Old, unused images can quietly rack up storage costs. Setting up lifecycle policies in ECR allows you to automatically expire and delete unused images based on tagging or age criteria. To run containerized applications in production confidently, you need more than just orchestration. You need deep observability. Let's begin with Amazon CloudWatch metrics. ECS automatically emits key metrics like CPU and memory utilization at the task and service level. These metrics are crucial for understanding performance, setting up alarms, and enabling auto-scaling based on real-time demand. For application logs, CloudWatch Logs is your go-to. You can route logs directly from your containers into centralized log groups, making it easy to search, visualize, and retain logs for debugging, audits, and compliance. You can even create metric filters from logs to trigger alarms on specific patterns. For distributed applications, AWS X-Ray offers powerful request tracing capabilities. With X-Ray, you can follow a request as it traverses different services, helping pinpoint bottlenecks, latency issues, or misbehaving microservices. In addition to system metrics, you can publish custom application-level metrics to CloudWatch. These could include business KPIs like queue depth, transaction counts, or error rates. Use CloudWatch dashboards to visualize these metrics and build a real-time operational view of your system. ECS also emits detailed service and task events, such as when a task is launched, stopped, or fails due to a health check. These events can help you quickly detect and troubleshoot service disruptions. AWS CloudTrail captures every ECS-related API call, offering full auditability of changes made to services, task definitions, and infrastructure components. Beyond AWS native tools, ECS integrates seamlessly with popular third-party observability platforms like Datadog, Prometheus, Grafana, and FluentBit. These integrations provide richer dashboards, alerting, and log aggregation features if you already use them in your stack. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.